Self-driving cars, Instagram filters, the heart of modern artificial intelligence. What does that have to do with people going downhill on a mountain? Well, stick around to the end of the video. Let's imagine a machine that receives a list of words and outputs a drawing that represents those words. The machine has two little knobs, and although we don't know exactly what each knob does, it definitely affects the output image in some weird ways. The machine also has a little screen that always displays a number from 0 to 1. This number represents how bad the drawing is, and we'll call it loss. Today, our objective is to make that number as close to 0 as possible, but how can we know what the best combinations for the knob values are if it would take a lifetime to test all the different possibilities? How about this? What if I took the knob values and put each one on an axis, then put the loss on the vertical axis like this? Now every knob combination has an altitude that corresponds to how bad the drawing is, and every time I test a new combination, it reveals a new point on the map. If we could test all of them, we would see the complete graph, but that would take too much time and energy in a real situation. So instead of trying to compute every point, we'll drop a little explorer at a random location on the graph, and we'll tell them to find us the lowest valley in the area. Of course, they can't see the ground because neither can we. So while a real person may try to feel the ground with their feet, our mathematical explorer will use partial derivatives. You can think of a derivative at a point as the slope of the function at that point. In our case, our point is defined by many different parameters, so we'll take the derivative with respect to each parameter individually, hence the name partial derivative. Putting the partial derivatives together into one big vector gives us the gradient of the function. In this example, the slope in the direction of p1 is very high and pretty low in the direction of p2. Because of this, the gradient vector of that specific point may look like this. We can use this vector as a sort of compass needle, an arrow that will guide us in the direction of steepest descent. Now we can take a step and update our coordinates to that new location. Repeat this process a bunch of times and you'll end up converging towards a locally minimal region. Notice that if we take a look at the broader picture of the graph, there are many other paths which lead to equally good or even better local minima than where we converged. But keep in mind that while applying this algorithm, we don't have this clear view of the whole graph. So it costs energy and time for us to start in different spots. This was the best that we could achieve by starting in this random location. Had we chosen another random starting spot, we might have ended up in a much better or worse local minima. But hey, it's a numbers game, and this is the best that we can do anyway. This algorithm is called gradient descent, and it's actually what most modern AIs use to learn. This is because we can take the millions of parameters, put them all in a million-dimensional graph, and descend in the same fashion. So every time you see a self-driving car, remember that they learned all of that using a lot of multivariable calculus, not just black magic.